You ever wondered why a simple ruler can feel flimsy one second and then incredibly strong the next? Well, it's not magic. It's actually a hidden property of its shape, a secret that engineers use to build just about everything from skyscrapers to bridges. In this explainer, we're going to uncover that exact secret.
So let's start with a really simple puzzle, one you can probably try right now at your desk with a ruler. If you lay it flat, right, and you press down in the middle, it flexes pretty easily, doesn't really put up much of a fight.
But now, flip that same ruler up on its thin edge. All of a sudden, it's incredibly stiff. It's the same amount of plastic, it's the same length, it's the same everything, except for how it's oriented. So what in the world is going on?
Well, like I said, it's not magic. It's a principle called moment of inertia. And it's the reason engineers can design these massive, efficient structures, like this monorail track, to carry just incredible loads without even breaking a sweat. Today, we're going to figure out exactly how it works. So that little puzzle with the ruler, it really gets to the heart of a central question in engineering. How do we build things that are both super strong and efficient without just, piling on more and more material? And here's the big takeaway. Strength isn't just about how much stuff you have. It's about where you put that stuff. The geometry, the actual shape of an object is often way more important than what it's even made of.
Okay, so this brings us to the core principle that really governs all of this stiffness. Let's give this idea of geometric strength its proper technical name.
The hero of our story today is a concept called the moment of inertia, or just MOI for short. In engineering, this is basically the technical term for a shape's stiffness. It's a pure property of the geometry that tells you exactly how well a cross-section is going to resist being bent. Now, to really get this, let's compare it to something we all know, area. Area tells you how much material you're working with. Simple. But moment of inertia, that measures the effectiveness of that material's layout. It's all about how spread out that material is. And just look at the units, length to the fourth power. That little number is a huge hint at just how powerful this property really is. And this right here, this is the secret sauce. Every little bit of a shape's area helps make it stiff, but its contribution gets multiplied by its distance from the center, squared. That means that material way out on the edges is exponentially more powerful at resisting bending than the material that's just sitting near the core. Okay, so let's see this whole principle in action. We're going to use what we just learned to basically invent one of the most important, most common structural shapes in the entire world. Let's say we start with just a solid block. Sure, it's strong, but it's also incredibly wasteful. All that material that's huddled close to the middle, it isn't very far from the bending axis, so its contribution to stiffness, that super important moment of inertia, is teeny tiny. It's basically just dead weight. So an engineer is always thinking about efficiency. How do we make this stronger without making it heavier? Or how do we make it just as strong but with way less material? Well, the logical first step is to just carve out all that lazy, ineffective material from the middle. You save cost, you save mass. But here's the clever part. We don't just throw that material away. We strategically move it to the top and the bottom, as far from the center as we can possibly get it. By creating these things called flanges, we have just dramatically boosted the moment of inertia without adding a single gram of new material. And just like that, we've created the iconic I-beam, an absolute masterpiece of structural efficiency. So, how do engineers actually calculate the MOI for more complicated, built-up shapes like our I-beam? I mean, they don't have to start from scratch with complex calculus every single time, right? Nope. They have a really clever tool for the job. They use this powerful formula called the parallel axis theorem, and you can really think of it as an engineering with Legos principle. It lets you treat any complex shape as if it's just built from a collection of simple, easy-to-calculate pieces. It's a really elegant four-step process. First, you just break your complex shape down into basic components, like rectangles. Then you find the MOI for each of those simple parts, which is super easy. Then you use the theorem to figure out how much extra stiffness each part adds based on its position. And finally, you just add it all up. That's it. And to keep everything neat and tidy, engineers often just use a simple table, just like this one. It makes the whole process really clear and totally repeatable. For our I-beam, you'd calculate the values for the top flange, the bottom flange, and that middle web, and then just sum the columns to get the grand total MOI for the entire shape. But of course, things get trickier. What happens when a shape isn't all nice and symmetrical like an I-beam? What if it wants to bend and twist in all sorts of weird ways when you push on it? Take an L-shaped beam, for example.
It's not obvious at all which way is its strongest orientation and which is its weakest. If you push on it from the top, it's probably not going to just bend straight down. It's going to want to twist, too.
Well, it turns out that every single shape, I don't care how complex it is, has a kind of true north for strength. These are called the principal axes. Along one of these axes, the shape has its absolute maximum possible stiffness. That's its Imax. And then, exactly 90 degrees to that, it has its minimum stiffness, its Imin.
So how do you find these hidden axes? Engineers use this brilliant graphical method called Moore's circle. You can basically feed it the stiffness properties along any two random directions, say horizontal and vertical. And this diagram then acts like a compass, rotating those values to magically reveal the true north, the exact angle and strength of that shape's strongest and weakest axes. It's an incredibly cool tool.
Okay, let's bring everything back to the world around us. We started with just a simple ruler, but this one principle is really the foundation of so much of modern civil and mechanical engineering. Moment of inertia is the silent, invisible hero holding up our world. It's in the beams of skyscrapers, the wings of an airplane, the massive girders holding up a bridge. It's even in the simple bookshelf in your room that sags a whole lot less when you stand the shelf up on its edge. This principle is absolutely everywhere once you know what to look for. So the next time you see an I-beam at a construction site, you'll know it's not just a random hunk of steel. It's a masterpiece of efficiency, carefully designed to put every single bit of its material exactly where it can do the most possible work.